Hello and a warm welcome. I am Armin Trost, Professor for Organizational Behavior at the Furtwangen University in Germany, and this is my course on social research methods. So, hello everybody. It's a while since I produced my last episode in this particular series. And I promised that I would continue a little bit more into statistics, and I would like to start with some thoughts around inferential statistics. And the first thing that I would like to explain in this particular episode is everything around estimating population mean, population, the standard deviation of the population. It's going to be about mu, about sigma, x bar, and all the like. And for some students that might sound a little bit confusing on first sight. But when you have a closer look, it turns out to be extremely simple. So, I mean, what do we do in statistics? We estimate, right? We estimate the truth. Why do we estimate? Because very often we don't know the truth. I mean, to give you an example, as I told you, I produced this series in the midst of the COVID-19 pandemic. And there's simply no truth that we are aware of regarding how many people are infected. We simply don't know. Or when we want to know what is the intelligence of human beings, of all human beings. What is the average intelligence of people? We simply don't know. We can't know. I mean, to find this out, we would have to measure all, right? But we rarely do. I mean, sometimes you measure something with an entire population. I mean, when you, for instance, measure something in your class, when your class is the population, okay, simply measure everybody, and then you don't need to estimate, then you have the result. So when you want to know what is the average grade on economics in your class, I mean, that's simply to be done, right? But very often you cannot measure the entire population. So we have to estimate. We have to estimate, okay? So, we assume that in a given population, whatever it is, all human beings, all Germans, all students in the world, whatever the population is, we assume there is a population size, which is abbreviated by capital N. That's the size of the population. And we assume there is a true mean in that population, which we don't know, but there is a true mean, right? And we name this mean mu. Mu. Yeah, it's this strange little sign here, mu, right? And we also assume that in this population, the values spread somehow around the mean, which is mirrored by the standard deviation of the population, which we also don't know. We don't know it, right? We don't know this standard deviation of the population. And we name this standard deviation of the population sigma. Okay, so whenever you hear about mu and sigma, these are the things that we want to estimate and which we, in most cases, don't know. We don't know these things whenever we draw a sample. When we just know the sample, but not everybody in the population. So, on the right side on this picture, which I show here in this lecture, is you have the values in the sample. And the sample size is small n compared to capital N. The small n indicates the sample size. So let's say we have 100 people pulled from the sample, and we make our measurement based on those 100 people, whatever we measure. And what we get then, and that's the easy thing, I mean, everybody can do it, you can calculate an average, a mean, right? A mean of the value x. And the mean is indicated by x bar. It's the x with this bar on top, right? And we can also calculate a standard deviation of the sample, which is small s. right? So the first thing you need to really take home is that there is mu and x bar, and there is sigma and standard deviation s. And the difference between these things is simply that mu is the real mean in the population, and x bar is the mean that we get based on the sample. And that might not be the same, right? It's very often not the same. It's just, it's a slight difference, right? And the standard deviation S of the sample is not equal to the standard deviation in the population sigma. So this is something that you need to take home, that this is different. One is the truth and one is the estimation. Okay? So now the question is how we estimate these things. And there is a simple idea in statistics that we say, okay, X bar is a good or the best available estimator for mu. In fact, it's not necessarily the same. But it's an estimation. With X bar, we estimate the true mu. Yeah. So, let's say we have the citizens in a country, and I take the example of Germany. Germany has 180 million citizens, and now we pull a sample of 1,000 people, and we make a PCR test, and then we learn that 11% are infected by COVID-19. Right? So then we assume that yes, in the population there are 11% people infected. Maybe in reality there are 12% or 10%, but we don't know. Why should we question 11? 11 is the best thing that we have, and there is no reason to assume that, okay, in the sample we found 11%, but maybe it's 12. No, probably it's closer to 11 than to 12, because 11 is what we got based on the sample. Okay, so with X bar we estimate mu. Okay, simple. Right? Now comes the tricky thing. How is it with the standard deviation? I told you in an earlier episode how to calculate the standard deviation. And when you really make a measurement based on the entire population, yeah, measuring the grades in economics in your particular class, okay, then you have the entire population in front of you, all the 100 people. And then you want to calculate the standard deviation of this particular population. Okay, just calculate the standard deviation. And you learned earlier how that goes. It's a strange formula where you sum up the deviation from the mean, you square it, and then you divide it by the size of the population, then you take the square root. It's a kind of average, right? It's a kind of average. Yeah. And when you have the entire population, right, simply calculate the standard deviation. Then you have the real standard deviation. Perfect, right? But now, when you just have a sample, the formula looks a little bit different. And then we say the standard deviation is just like the standard deviation it's just calculated like we always do with standard deviation. But in the denominator of this particular formula, you find not n, but n minus 1. N minus 1. And that is something that you do when you want to estimate the standard deviation of the population based on the sample, because you do not have the entire population in the data set. And now, here's the thing. You ask, why n minus 1 in the denominator? And really, when you want to bother your statistic teacher, your statistic professor, raise your hand and say, hey, professor, I have a question. Why n minus 1? Huh? And then, I promise you one thing. You're gonna get, the probability is high that you're gonna get a very weird answer, really, as I got when I was a student. I must admit that it took me very long to understand why it's n minus 1. And you know, you always get an explanation, you very often get an explanation by your statistics professor saying something, talking about degrees of freedom and blah, 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 blah. And then you say, okay, I understood this degree of freedom thing, I think, but still does not make sense to me why n minus 1 and not n. And sorry, I don't get it. It really. So, I would like to share with you why this is the case. And what I did is, you know, I earlier created a population. I simulated a population of a few thousand cases, right? I just did it in Excel. I simulated a normally distributed population with a normally distributed parameter. Don't need to tell you how that goes, but you know, it's the idea that I have a real population in front of me. I have it in Excel, and I really know the true mean of this population because I created it. I played God for a moment, and I really know the true standard deviation in this population. I know it. So mu in that particular simulated population is 3.01. Why is it? It's just the case. It's as it is. And the standard deviation sigma is 1.22. Okay? But now let's assume we do not know the entire population and we have to pull samples. So this is what I did. I pulled 10 samples. And in one time I had a sample size of 20. And one time I had sample size of 8. But now let's look at the sample size of 20. So imagine this. I have this many thousand cases in this population and I randomly pull 20 cases. Randomly. I can do this in Excel. It's easy. And then I calculate the mean based on the sample and I calculate the standard deviation. Right? And sometimes I use n in the denominator, like in sigma, or I use S, the estimator for standard deviation with n minus 1 in the denominator. And now what do I get? When I use just n, I will find that the standard deviation that I get based on the sample are very often too small. So when you use n in the denominator of the standard deviation formula, then probability is high that the result you get is lower than the real one. You underestimate the standard deviation. And why is that? I mean, now here are some mathematical explanation, but one explanation is that when you just pull a sample, you very often do not have the extreme values, but the extreme values, they increase the standard deviation to a large extent, but because you don't have it, you very often find standard deviation that are smaller than the real ones, right? So what do we do? And when you see now, when you take a smaller sample, not 20, but just 8, you find that you even more underestimate the real standard deviation. You always constantly get values that are too small, like in my simulation. So here's the trick. When you want to estimate the standard deviation based on a sample, you don't have n in your denominator, but n minus 1. So having n minus 1 makes the result slightly bigger, right? And the bigger is the sample, the smaller is this effect, right? So this n minus 1 is just a trick, you know? Sorry. It's just a trick. It's a little adjustment. That's all. That's all what you do. A little adjustment. So to come closer to the real standard deviation that you don't know when you just have a sample. Okay, that's the idea. So far we were talking about estimating mu, estimating sigma, right? Now, Let's assume the following. Now we do exactly what I was talking about. You have a population and you constantly poll a sample many times and you calculate the average based on the sample. You do this over and over and over again. When you do this, you get many means, right? For every sample you pull of this population, you get a mean, right? So now, when you pull a lot of samples, right, over and over again, right, and you calculate the average based on the sample, these values distribute somehow, right? They distribute. And how does that distribution look like? Now we ask ourselves, how is the distribution of the sample mean? What we do know is that the mean of the sample mean, or the mean of the sample mean, did you get it? I mean, when 20 times you take a sample and calculate a mean, then you get 20 means, and now you calculate the mean of the 20 means. Then you can assume that this mean of all the means, yeah, in the end is equal to mu. It's equal to the average in the population. Okay, but how is it with the distribution of the sample mean? How do all these sample mean distribute around the mean? And now you can assume that this distribution is significantly smaller or more narrow than the original distribution of all the cases in your population. And now here's an idea how you can calculate the standard deviation, how you can estimate the standard deviation of the sample means. And there is a simple formula that we use. It's simply that we have a sigma for the sample mean is equal to the sigma of the distribution divided by the square root of the size of the sample. Right? It's a simple formula. You don't have to understand it right now, but it's something that we really need. Right? And it's something that we need when it comes to inferential statistics. Okay? So, as far as now, you have understood the difference between sigma and standard deviation of the sample. You also have understood the difference between mu and the calculated average of the sample x bar. Right? You have understood why, when it comes to estimating the standard deviation just based on a sample, why we use n minus 1 in the denominator and not n, right? And you have understood that there is a way to calculate the distribution of the sample mean. And that's something that I'm going to refer to in one of the next episodes when it comes to inferential statistics. Okay, so much for the moment, and I hope we see us in the next episode.